Let's behave now.
All right, welcome back. So we have the second lecture by Rosie.
All right, seems a little bit cooler in here this afternoon, so hopefully this will make things a little easier. So I'll give you the second part of my introduction to experimental physics. So this is just my outline again. So I'll be talking about calorimetry, particle identification. Okay, I didn't put these in order. I actually decided to leave most of the far forward, far backwards for my good colleague Alex Ganch, some physics and interaction region considerations. So let's start off with PID. So one of the things we want to know when we have a collision and some particles fly out, okay, we talked yesterday about how we want to know their kinematics, so their momentum and their position. But we also want to know what type of particles are they? Whether they're protons or kaons or pions. And so there's a lot of considerations that can go into this. And so what this plot here shows, and I'll come back to this plot a couple times. This is the separation between kaons and pions at the 3 sigma level. So this means you really have a 1 in a million chance of getting, or 1 in a million, I guess. So the three sigma is 1 in 1,000. 1 in 1,000 chance of getting them confused. Math is hard, but this is versus the momentum. So this gives you the separation at 3 sigma, which is a nice separation. And then this is versus the required detector length. So at some level, you could build a big enough detector that you'll be able to separate your kaons and your pions to any degree. But then, of course, you have all these other considerations in terms of what you need to do. So this shows a variety of technologies that we'll talk about, from the rich detectors, from time of flight, and other things like this. But this really is sort of the trade that we have to make when we're designing an experiment, is what technologies we can use, and how big are they, how expensive they are, how much material they added, and that can be an issue in terms of your ability to do that. So I won't be able to cover all PID technologies that exist, and I will cover one that isn't being used in EIC physics, just because I think it's a useful one to know. There's also, for instance, other ways in which the identification of a particle can be used for something that using detectors that aren't dedicated PID detectors. So for instance, the electron ID can be determined by matching tracks with calorimetry. Also, and I'll talk about this a little bit, the ionization energy loss. So DEDX and detectors like time projection chambers can also give you both PID and kinematic measures. So it's rare to have a detector that only does one thing, and that's all it does. Usually you want them to have a multiple things that they can accomplish. So I'm going to talk about time projection chambers just briefly. So I have here a picture of the sPhoenix time projection chamber before we put all the cabling that I was showing you guys this morning in my photo from my cell phone. But the way a time projection chamber works is you have a volume of gas, charged particle goes through it, it ionizes that gas slowly drifts to the readout due to the electric field. And so what you get is the XY coordinates as things are being read out, but as it drifts, as they drift, you get essentially its Z coordinates. So this is just if you know the speed at which the ionization is drifting, and you know how long it took, you thus know where it happened in Z. So this gives you a 3-dimensional projection. This is why it's called the time projection chamber. And this is very useful for solenoidal fields, because you can have the electric field and magnetic field are of course parallel to one another. So you this works well in giant solenoids, which is basically describes Alice, star, and sPhoenix. Now one issue is that so you read things out at the end. So I'm showing here just the picture of the sPhoenix TPC, and the readouts are at the endpoints. And you need to be in a configuration that suppresses ion backflow. One could talk about TPCs for an entire hour, and in fact, I taught my advanced particle physics class. I invited an expert. He did give us an hour-long conversation. They're very complicated, but very interesting. Another issue with high projection chambers is that as you have this ionization drifting across, another collision will happen and another collision will happen and that ionization will drift. And you can have so much ionization in your TPC that now just due to the charge of the gas, you're essentially distorting now the particle paths as they go through. So instead of seeing something that looks like a nice straight track, you'll see something that's curved or in some fashion. So the way in which one calibrates these is hard. Now, why would we why are TPCs used? Well, it's a big volume of gas. So this has very low material budget. This is something that, of course, is very useful if you want to for tracking. So silicon, of course, if you have a solid, if you have electronic boards, it's more material there, so that disrupts your particles. And if you have enough hit points, you can really get this nice PID distribution. So what I'm showing in the plot here, this is the ionization energy loss in the TPC versus momentum of the particle divided by the charge. And you can see these beta block, curves like that we looked at yesterday, but you can see now since they're all, instead of with different materials, they're all in the same material, because this is all from the time projection chamber, but it then separates them out by species. So you can see here the electron band, pions, kaons, protons, deuterons, tritons. They even got some helium-3 particles that they're able to determine just based on this. And this actually shows one nice aspect of this plot is it shows one of the fundamental issues if you try to only use one technology for your PID. You can see if you have a particle that has this ionization energy loss and this momentum right in here or in here, maybe in here, that there are multiple species that it can be. So these bands are overlapping. And at that point, all you know is it has an ionization energy loss that could make it a kaon or could make it a pion or a proton. And you can also see here the distributions, like one issue, and these are the pions here in the dark band, is that there are a lot of pions. So they can really disrupt a lot of measurements when you want to measure something where you prefer not to have a pion. But we aren't using a time projection chamber for the EIC. And I think that's mainly just due to the slow speed at which these detectors operate. All right, so let's talk about what we are using. So there's so I repeat this plot here. So this is our basically momentum of the particles, the required length of the detector to measure all of these. And what we really want to do is we want to determine and be able to separate electrons from photons. We want to be able to separate electrons from charged hadrons, because if you recall, nearly every measurement that we're going to make is going to be, I measure the kinematics of my scattered electron plus stuff. That probably describes, well, 70% of the physics. There may be someone who would dispute that. But another thing that's really important is determining the difference between pions, kaons, and protons, especially the separation. So the kaons and the protons have fairly similar mass. They're all charged hadrons. Okay, pi zero is a separate case we'll talk about. But they're all charged hadrons, so leave a track in your tracking detector and they'll shower in your hadronic calorimeter. So the picture I showed you yesterday where we're all like, okay, we know what everything is, it's actually harder when it comes down to it. So I'll repeat this plot again as well, but what this is showing is now the rapidity of the detector and the momentum along the z-axis. This is now showing events from some Pythia simulations. And basically these boxes are showing where each different detector technology we're using at EPIC will be able to do PID. And so you can see that and the boxes are overlapping on purpose. I wasn't just sloppy with my PowerPoint. There is regions where two PID detectors overlap. And so this is really trying to separate now pions and kaons at the 3 sigma level. So basically, we really do need more than one technology to cover the entire momentum range and the entire rapidity range in order to have our PID. So we'll talk now about the different PID detectors. So I show you again a picture of EPIC. The electrons, I didn't copy my arrows, but the electrons are going this way and the hadrons are going this way. So what we have here is the proximity focused rich, so the PF rich. So we have that in this area. We have the dual radial ridge, the D ridge here. The ACL GAD, which I mentioned yesterday, and I guess I still kept the arrow black by accident, is here in the center. And then on the outside, we have the HP DIR. And I'll talk about each of these technologies and how we use them. So first, we're going to talk about shrink-off counters. So we know shrink-off light is emitted when the velocity of a particle going through the medium is faster than the speed of light in that medium. So this is perfectly allowable. And so basically you get what's likened as sonic boom, but it's an optical. And so light is emitted and it has this characteristic angle that's related to the index of refraction of the material and the velocity of the particle itself. So this beta is greater than 1. And so you'll have some particular angle, and because the angle depends on the velocity, you know exactly the velocity of the particle based on this angle. And then you know the different, then you can measure the momentum of the particle and thus you get the species. And so this is actually, so this picture here is one of my favorites when I talk about shrink-off radiation. This is actually shrink-off radiation from a nuclear fission reactor core. So the Simpsons got it wrong. Radiation isn't green, it's blue. So, but that's a pretty often described as a very pretty blue light. So one thing you can do is you have a threshold counter where you're just, okay, do you see the light at all? Yes, and it triggers. Another aspect that we'll talk about is ring imaging shrink off. So this is a rich detector. And so I say there's an angle as the particle travels, there'll be a ring of light that comes from the shrink off radiation. And we can actually use this to measure the type of particle. There's actually typically only a few photons that come out of this. So it's not like this bright ring that you can like really see. So this makes the measurement quite delicate to do. And so this is actually used in a lot of technology, not just the EIC. This is used in these underground counters. So that where they're looking at like for neutrinos and such. So I have here this one of my favorite pictures as well. This is a super Kamiokon. And so this was their giant vat here. These little things that you can see, these circles are the PMTs that were to read out the light from shrink off radiation. And here they were looking for solar neutrino oscillations. So essentially measuring electron neutrinos and showing the oscillation that you get the expected yields of electron versus muon neutrinos. And I do find the solar neutrino problem is one of my favorite lectures to give in class, but I won't go into that here. And so I have here then a little bit of the diagram. You could see both up here, the circle that you would get if you have a neutrino, it hits something that's charged out, now it's moving through your material. You kind of get this ring of light here that you can determine the exact velocity of it. And this is also used to look at particle showers in the atmosphere and other situations. So this is a broadly useful technology for identifying particles. And so we use it in different ways. So the first of the detectors we'll talk about is the PF rich. So this is just proximity focusing rich. So this uses it's a shrink off radiator. It has 2.5 centimeter thick aerogel. So this is an index of refraction of about 1.04. So you notice all of these have index of refraction close to 1. It has an acrylic filter. And the idea here is that it produces on average, we have a particle of about 11 to 12 photoelectrons. So this is just the signal that you may receive in your electronics. Now, one advantage is that this gives you timing resolution less than 20 picoseconds. So this will help you distinguish your particles. So I repeat the equation here, and then I show a plot where this is now showing you the shrink off angle versus the momentum of the charged particle. And you can see, just as I showed you with the TPC, this different bands for the different particles. So this allows you to see which particles went where in this particular detector. And you could take a slice, for instance, in a particular distribution, and you can look at so this is taking a slice this way and looking at the distance between them. So So you still, with this technology and all technologies, you can see as you go up in momentum, everything kind of comes together and that makes it difficult. So it's very easy to do PID for low momentum particles. It's much harder for high momentum particles. So we have another technology here. So this is also a shrink off light generator. So this is the HP DIRC. I think it's the high performance DIRC. Seems a little bit hubris, when you tell you're going to call your detector high performance, but it gets you high performance computing and things like this. So I don't know what we'll do in a generation. We'll have to have like super duper performance. But this is the acronym here stands for the detection of internally reflected shrink off light. So the idea is you have you set it up so you know the particular angles in which the light is going to be striking. It's shrink off light, and you set up some mostly clear, low index of diffraction. If you're curious, in this case, it's they're called the radii bar. But you set it up so you have tonal internal reflection. So if you recall from your freshman physics classes, light is passing from one index of refraction to another particular angle. It can be tonally internally reflected and just bounce down. So it'll just keep bouncing back and forth down the radiator out to the readout areas. And so this allows you to do precise particle identification. So it has 3 layers of lenses. It has this FACS photo detection. So one of the things I'm not going to discuss today is how we do photo detections. This is using PMTs, which are photomultiplier tubes. So that'll remain magic until someone else covers them. And this here is just a plot that shows the difference between the polar angle and the separation. And this is showing the separation between pions and kaons, and then electrons and pions at this values. The last of the technology I'll discuss here is a dual radiator rich. So this is also a ring imaging shrink off detector. This is also using 2 different gases, so the aerogel and C2F6. I probably should have put little numbers in the lowercase. Don't tell my chemistry professors. These have very low index of refraction, and then you have mirrors that reflect the light and allow you to determine precisely where the particle is. So this here is a simulation of a sample event. So we use Géant to determine where the particles are going, and from here we can do some PID. So we can talk about time of flight, but before I do that, and this is something I've kind of touched on a little bit in a couple of different points, even yesterday, not so much today, is this idea of an avalanche. And so one of the issues when you have a signal, you often want to amplify the signal so you can really have a chance to read it out with your electronics. So what this is showing is you have some detector with some drift region and some incoming ionizing particle. This could be silicon, this could be a TPC, this could be whatever you like. We talked about it in terms of the mass tracking, for instance, yesterday in the MGADs. And so then you have some boundary between the region where your ionization is and then your readout. And so if you set up a situation where every electron that comes through will avalanche by producing electrons and photons, and those create more and more. For instance, if you have an electric field is usually how this is done. Then at the readout sensor, you actually end up getting a lot more electrons than you produce by the ionization. This is an important process. So this is, for instance, used to okay, not quite like this, but you get something similar in, say, photomultiplier tubes. This is mostly here for gaseous detectors. You have this long equation here that we won't have to go through, but the idea is that you end up having a big enough range and a large enough difference in operating voltage that you can get some significant gains. So this means even for things like shrink-off detectors, where you only have a handful of photons, you actually can make a significant measurement. And this becomes somewhat important for the ACL GAD. Now, this is a slightly different type of technology. So for the shrink-off radiation, we're really determining the velocity because it's based on the angle of the light. But for a time of flight detector, what we're doing is we're measuring how long it takes the particle to go from the primary collision to the detector itself. So this is just if you measure the time and you know the momentum from your tracking detectors, then you know the velocity. If you know the velocity and the momentum, you can determine the mass. So this is the AC LGAD. This is a low gain avalanche diode. So the LGADs have been around a while. The difference is this is AC coupled. And so what this means is you don't have a direct electrical connection between the detector and the readout electronics. So you have this insulating layer and you couple it via AC. But this operates as many of the other particle detectors we've seen. You have a charged particle that goes through the detector. It generates electron hole pairs. And then you have this very high electric field in the LGAD layer, which amplifies the signal. So your avalanche that I showed on the previous slide will be there. And then this induces a signal on your electrodes, which then can be read out. So the idea here is that this is very precise and fast. So we actually have two AC LGAD layers. So one is in the barrel. So this is the central part here that you can see, and the other is in the forward region. These are done in 5 micrometer by 1 centimeter strips. So you know the timing in the strip. One advantage to EIC collisions, of course, is that they're not like heavy ion collisions where you have thousands of particles coming out. You have handfuls, so you can get away with strips a bit more. Another useful aspect is that it has very low material budget. So the barrel is only at 1%. The forward detector is at 80%. This is slightly more pixelated than strips. So you can see here, the particles are largely aiming in this direction. And so this actually, the detector, the ACL GAD will give you a spatial resolution of about 30 micrometers. That's good. And time resolution on the order of 25 picoseconds. So it's very fast. So that's faster than the collision rate will be in the accelerator. And then we have here some distributions. So now if you're looking at particles, you see bands of different particles. This is looking at them versus beta, so the velocity. So this is the barrel layer and this is the forward layer. So you can see here, we can tell the difference between electrons, of course, basically travel at the speed of light as far as this is concerned. But you can see the difference between pions and kaons and protons. And so this allows you to distinguish between these different particles up to a certain momentum. So for instance, you could distinguish electrons here in blue and pions here in orange up to about 0.5 GeV in the barrel layer and up to about 0.8 GeV in the forward layer. And so on. So you can look at, so if you want to say distinguishing kaons from pions, so you can see that the green and the yellow overlap over here and so on. So this just shows versus pseudo rapidity, the 3 sigma separation that you can get versus momentum. So this is just where, and you can see the various cutoffs in terms of this distribution. Oops. Okay. No panic. And then you can see here that there's actually a different distribution as you go in Eta in the barrel region. But it's pretty flat with pseudo rapidity for the forward region. So this will allow you to do all of the PID that you would like in terms of measuring now what's an electron, what's a pion, and so on. So we come back to this, which I think is quite important. So if you're a physicist who's now going to do an analysis and analyze the data coming out, you actually do have to learn how to use or how to interpret the data from all of these detectors. And they were chosen based on many considerations. So one is speed, another is radiation hardness. Another is how much it costs to build a detector of a certain size. So another is space concerns. And we'll talk a little bit towards the end about like various things that have to go into determining your technologies. But there's no possible way we could just pick one type of detector and have it work in the entire detector. So for instance, you can see here time of flight is quite precise, but you would need a much bigger distance for time of flight. So if we just talk about this for a second, usually you put tracking layer and then your time of flight layer to give some distance between where the collision has happened and where the time of flight detector is. Then if you think about the time of flight's measuring a distance, the shorter the distance it has to measure the time over the more precise the timing has to be. So it's like if I'm sitting here with a stopwatch and you only have to run, want to see how fast you can run and you run 2 feet and I have to click on and on the stopwatch, it's gonna be very difficult. Whereas if I take you to a track and have you run a mile, I could very much determine your speed, ignoring the fact that probably you can run faster over 2 to 3 feet than a mile. But, all right, so that's particle identification. And I want to cover one more thing before we talk about calorimeters. And so this is just scintillation counters. So scintillation, the basic idea. So one of the things that we have to do is almost all of our detectors create photons in the process of the particles we care about going through matter. And what we want to do is we want to read out those photons in some fashion. So we want to make our measurement by reading the photons. So one thing we do is we can use scintillator. And so what this does is this converts the ionization to light, essentially, and then it allows you to collect the light. So usually you have like a plastic. So this is actually what's here. I'll talk about this in a minute. But you can have plastic or oil, which is doped with a fluorescent chemical. And so the passing of the radiation excites the molecules, and then they vibrate, and then that gives you light, essentially. And so one nice thing is that the material is transparent to its own radiation. This is very useful. And what this allows to have happen is the UV light ends up being shifted to visible light. And so this is sort of the picture I have here is of a piece of the S-Phoenix event plane detector that we built. We built one for STAR and one for S-Phoenix. And so this is one of my students here, and we actually were playing with UV lights. So normally this detector has dark paper over it, so you don't want light from other sources. But we were having fun in lab one day. So this was a fun detector to build. It was largely hand built by undergrads and graduate students. So but you can really see, shining UV light on it that you can see all the glowing here. And these green fibers here, those are wavelength shifting fibers, which is an exciting thing that I can't tell you about in this lecture. It'll be 2 hours long. So here's a reminder from yesterday. We talked a bit about electromagnetic showers. So this is if you have an electron, it goes through material. It will basically double every radiation length. So you have your electron emits a photon. That photon will produce an electron-positron pair. Those can then emit photons and so on. And you have this doubling of the number of particles until they're absorbed, basically. So then we collect the light here to determine the total energy that the starting particle happened. And the critical energy is where electrons and positrons, instead of pair producing and emitting Bremsstrahlung, are really just losing energy via ionization. And so your typical resolution of electron calorimeters is on the order of 3 to 10% per square root of E over G. So this is just some rough estimate. We also talked about hadronic showers yesterday. So hadronic shower is now essentially the same thing, but with QCD. So you have a hadron, it goes through some high Z material, it interacts via the QCD force, it gives a shower. The showers tend to be a lot bigger, as we mentioned yesterday. And so this means you need a bigger detector to contain all the energy. There's also the issue of electromagnetic showers. So when your hadron is splitting into pi plus, pi minus, and pi zeros. The pi zeros immediately decay to 2 photons, and so now you have an electromagnetic shower as part of your hadronic shower. This is all stuff we discussed yesterday, but now we want to talk about the actual detectors and how they're being used. But let's first talk a little bit about energy resolution calorimetry. So here I just wrong button, went too fast. So here I'm just showing an approximate distribution. So this is just the sigma of energy compared to the energy of the particle. So, if you have a 10 GeV particle, it's a question of whether you measure it being 9 or 11. And so that's the resolution. So we actually have a couple different terms. We're really talking about now a physical calorimeter rather than this sort of perfect calorimeter that might live in our minds. So the stochastic term is the one that we often talk about in textbooks. So this is this A term here. And this is just due to fluctuations in the number of signal generating processes. So, and you can see, I'll learn which button to push. I show these different radiation lengths, but this is actually a statistical process. It's not like the electron goes precisely one radiation length and then emits a photon. And then that photon goes precisely one radiation length and then pair produces. This is just sort of an average quantity, and not everything here is statistical. So sometimes if you were able to line up, and just shoot with a particle gun, electrons of a given energy at the calorimeter, even if they're exactly the same energy every time, what you would measure would be a little bit different just due to the fluctuations that you can have. And this is unavoidable. So this uncertainty here, the stochastic term, there's nothing you can do to make this better, because this is just the way quantum mechanics in the universe works. Now, there's other terms here. So this is another term is the noise term. So this is noise in the readout electronics. Another thing I can't discuss too much, but basically all readout electronics have some inherent signal in them that we try to remove via, for instance, things you might hear things like pedestal subtraction. So this is where you measure the signal in the detector without any without any beam going through it. So basically no signal. You see what your electronics do. You can say, oh, there's always the signal, and there's other things you could remove it. There's also an issue from pileup. We discussed pileup a little bit yesterday, but this is if you have more than one collision at the same time, you might have something else that goes through the calorimeter from the other collision. So this things like electronics noise, you can try to reduce. Other things you might not be able to do that. That all goes to this B term. And then the last term is this constant term. So this comes from imperfections in the calorimeter construction. So non-uniform response. So this means if in one area that you get more energy, so say, and here I mean more light out for a particle of given energy than in another area, that could contribute dead areas. Now these things are sectors, so there has to be some dead area to be able to you can't build it entirely. So there's always the area between pieces of the detector. But this all adds to this C, and you also want this to be as small as possible. And so the small constant term is something that we can beat down as well. And so in general, when you see a plus, this is from the CMS electromagnetic calorimeter, but you can look at it versus energy, and then this is the resolution. So you can see the resolution improves as you go up in energy. Okay. So EPIC has several calorimeters. I bring back the picture from yesterday of just the barrel systems. Now we're looking at red, so the EM cal. So we see here, we talked about the yellow detectors here, so the tracking detectors yesterday. And here we've discussed these are where the PID detectors are, so you can kind of see this aspect of things. Purple is the magnet, but red here is now the electromagnetic calorimeter. And so we really want to we really need to use electromagnetic calorimetry to measure photons and identify electrons. And so there's actually two different technologies. One is the barrel backward calorimeter. So this is tungsten and sci-fi. And then the other is the barrel imaging calorimeter. All right, so here's some details. So we discussed yesterday a little bit. We made, as a community, we came together several years ago. We wrote the yellow report. We're like, this is everything we need to do and how well we need to do it to be able to make the measurements we need at the EIC. This just lists a bunch of things that we need to do. Some of them, for instance, it has to survive a certain radiation dose. We already have some idea of the amount of radiation that's going to be generated. You don't want to make a detector that you put in and then immediately gets fried. That's always a critical component. You need to be able to have it operate so it can operate at the speed at which it's going to get hit, and so on. And then here we have then the resolutions that are required for the different aspects of things. So here you could see the constant term in each of these, and the noise term is essentially 0 for most of this, and then the different resolutions. Now the resolution has to be much better for the electron end cap than for the barrel or the hadron going side if you decide to build something there. And this is because you really want to find that scattered electron, right? So we come back to almost all of our physics can be described as we measure the deflection of the scattered electron and we correlate it with stuff. So if we don't know where that scattered electron is, we're out of luck. And one of the biggest backgrounds is distinguishing between pi zeros and photons. So we have So we'll want to know if we have, for instance, pi zeros going into the calorimeter, or if we want to, or if we have photons. So this really comes down to this issue of the pi zero decaying into 2 photons almost immediately. And so you can see here if the faster the pi zero is going, the narrower the opening angle between these 2 photons will be. And if they overlap in a single tower, you can't tell whether that tower was generated by pi zero or it was generated by a photon. And so this is called cluster merging. So this is something that's simulated and looked at. And you can see here that they list sort of from the yellow report up to what momentum of pi zero do we want to be able to distinguish the pi zero from photons. So here we just show some pictures of the different calorimeters. So in this case, we have the barrel imaging calorimeter. I'll talk more specifically about that. And then also the end cap calorimeter here for the electrons. All right. So first, the end cap calorimeter. So this is actually the calorimeter that I'm part of the team of. And so here we're using crystals that are lead tungstenate. So you can see here a prototype crystal. This looks like glass. I don't know, have any of you held a lead tungstenate crystal before? So if you get this, so we're back to, I should have rated BNL before coming here. Next year, I'll remember this. But so it looks like glass, but it's heavy like lead, right? So it's actually somewhat of a fascinating thing because your brain is used to what things should weigh. So if I handed you a piece of glass, your brain says, oh yeah, this is silicon. I have an experience with this. I know how much it weighs. If I hand you a piece like this, it's really very heavy. And of course, I know if I told you, oh, is lead or glass heavier? Everybody here would be like, oh, well, lead is more dense than glass, sure. But the fact that it's clear makes it hard. Now, one reason why you might want to have crystals like this is in terms of the readout. So I have here a simulation picture. So this shows some charged electron coming in and it starts showering. And in this case, it's showering within the detector as a whole. And so then you contain everything, you measure all of the lead that's come out. There are other calorimeters that do sampling where they have scintillator and then like lead and then scintillator and then lead. They can't measure the photons that are produced in the lead. If it's just regular lead, lead is not see-through, so you can't get the photons out of it. They're only sampling some of the energy. And from there, you have to infer how much total energy was there. But there's always these fluctuations that we discuss in terms of the number of particles. So you can you won't be able to, it's not quite as precise as building things with these crystals. But as you can guess, this is a big cost thing. I think the budget for these crystals is on the order of $15 million or something like that. I forget our precise total. We're still waiting to hear back from the NSF. And so what this calorimeter allows us to do is it allows us to give us some very nice resolution. So the crystals are a particular size of the molar radius. It allows us to suppress the hadron background. And we can really measure photons down to about 100 MeV. So very light, very low energy photons. This is very important for DVCS photons in particular. So this is deeply virtual Compton scattering. And also one of the things we may want to see, nearly everything in some level decays to photons. We want to measure decay photons and decay electrons. So there's been prototypes, and so even though the EIC is still many years away, things have actually been prototyped and tested in beam tests. So this is from a beam test in 2021, and you can see here the resolution from this particular prototype. And here we also have then from the measurements the probability of the pi zero merging. So this is, one can try and do some fancy games with the shower profile to try and divide this. So this is basically the best we can do right now, given current shower profile analysis. But this is actually a great yes.
What's pi zero merging?
So the pi zero decays to 2 photons, and then if they merge together, so if they're so close together that the pixels basically can't distinguish them.
Okay.
It really depends a little bit. So if you're in the pi zero rest frame, the photons are back to back, but the pi zero can be boosted in any direction. So if it's boosted in the direction of like one of the decay photons, you'll have no problem separating it. But if it's boosted sort of perpendicular to the decay, then the opening it. Yeah, so and then one can actually get, you know, if you have multiple towers, actually, if I go back a couple, so if you have multiple towers here, you can see this picture here that I rather like from the internet that essentially shows the extent, if you have a pi zero, isn't it actually extends to multiple towers, and so you might actually be able to do something clever with like AI to distinguish these things. So one of the things on my to-do list of things I might want to figure out how to do. But all right, so then the went too fast. Okay, we're here, we're going here next. Good. So then, and the hadron end cap, you still may want to have a calorimeter. So one of the proposals is to use the same technology as the cfns calorimeter. So this is tungsten plus sci-fi Spacell designs. So essentially you make these blocks of this is essentially tungsten powder with scintillating fibers in it. So the nice thing about this is the construction is relatively straightforward. We actually used so to make this calorimeter, we had teams of undergrads that largely built it. So what you would do is there'd be a frame that would hold these scintillating fibers. You would need one at the bottom and one at the top of the block, and they actually fit perfectly in a red Solo cup. And then you had to put the fibers through the frames. And now this is something that the older you get, the more blind you get, the harder it was. So the best people do it were the freshmen. And then once you get the fibers through, then you would put this thing into this matrix and you'd glue everything. You'd put the tungsten powder in, you pull the epoxy through, all sorts of stuff like that, machine the whole thing. But this allows you to make a fairly nice electromagnetic calorimeter. And here we have from our tests from Fermilab for the cfns calorimeter what the resolution was there. So this is our guess if we end up for the hadron end cap, what we would like to build for the electromagnetic calorimeter on that side. But this gives you a nice compact granular electromagnetic calorimeter that you can measure. And this is actually kind of interesting as well. These blocks look relatively not see-through. They're quite heavy, but if you hold them up to your eye because of the packing layer later fibers, you can actually see through them, which shouldn't be so surprising since we want to have light, but it's still kind of fascinating to wave your hand on the other side of one of these blocks. So the barrel will be a lead sci-fi imaging calorimeter. So essentially we have 6 imaging SI layers. So this is silicon. There's 4 layers in our baseline measurement. So this, baseline detector, there's still some work going on in precisely how this whole thing will be put together. And this is interwoven with your lead sci-fi layers. So in this case, you use silicon to image, basically much like a tracking detector to image where the particle is. And then you use these layers of lead to create the shower and the scintillating fiber to pull out the light. And then this is followed by a pretty thick lead and sci-fi layer at the inner region. This is going to be read out by these astropix, which I don't have time to discuss, but basically the point here is these were used for NASA's Omega X mission. And one of the things we like to do is, you know, you never want to necessarily invent something and be the first person to use it. So we often borrow from other either other high energy or nuclear experiments, but also, you know, astrophysics and stuff like that. So you can use these astropix chips to read out your detector. And I have here then the resolution that you can see from some test beams that have been done. So all of these are in some stages, at least some have been built. So then we can move to hadronic calorimetry. And so, oh, sorry.
What is the physics motivation for the barrel calorimeter?
So really, it's basically you want to be able to measure electrons and photons and pi zeros. So it's outside of the tracking layers. And so once the particle hits here, you know whether it's left to track. You know a little bit based on the CLGAD whether you have some PID information, but then if you get there and you see a tower with no track, you know it's a photon or pi zero. It's on. So, but this basically is really particle identification, for the most part. And one wants to, and if we talk about jets, which is my favorite topic in the world, jet, you want to gather all the energy for it. So you really want the different detectors to be able to measure both the electromagnetic energy and then the hadronic energy. So the hadronic calorimeter, so this will be on the outside. So this is actually already built, so that's great. So we're gonna use the hadronic calorimeter from S Phoenix. So this is a picture of it from a couple of years ago, completed. So it's this big blue steel thing. This is essentially a slice of S Phoenix. So S Phoenix as well had an electromagnetic calorimeter. Here we had an inner H cal, that's before the magnet. The magnet itself, which is the contingency magnet for EPIC. So if things go poorly, we might actually also have that magnet. But and then on the outside we have the H cal. And essentially the reason, so you have this projective geometry, and you see this also with calorimeters. We know the collision is going to be happening at the center of the detector. Particles fly out like this. You want your towers to be angled towards the interaction region, so that way when a particle goes through it, it stays in a single tower rather than crossing a number of them. But you can say, okay, well, why does it change directions? And then in this case, it changes. The top laser button occasionally like advances the slides. It's a little confusing. But this is because the magnetic field, it changes sign whether you're on the inside or outside in terms of which way the particles will curve due to the magnetic field. So this was actually largely driven by the jet physics we wanted to do at S Unix. So it had coverage out from pseudo-rapidity of -1.1 to 1.1. And it really can absorb about 95% of the energy from a 30 GeV jet. So this allows us to really measure the energy quite precisely for jets up to about 30 GeV. We can in fact measure them after that. They just have a chance of punching through the detector entirely. And we have here the requirements, at least for our hadronic resolution with of the combined calorimetry of this. So this was in central gold collisions. And that might look high. I just told you that hadronic calorimeter should have a resolution of 50%. And heavy ion collision, you have this like huge fluctuating background due to the ions colliding. And so that also messes with your resolution in a way that's pure physics and you can't beat with a better calorimeter. Okay, so this is our HCAL design. So yeah, I got to actually cable a bunch of it. So this was done, as you can tell, during the pandemic. So people basically had to run all of these cables through to be able to plug in the SIPMs and stuff like this. So it was a very labor intensive task. But it gave me something to do. And so each of these sectors, so these are the same blue sectors that I showed in the previous picture. They're 6.3 meters long. They weigh 13.5 tons. So you clearly can't lift them up. That's why these cement blocks. And inside are the scintillating tiles. So you can somewhat see this in the photo. So they're different tiles they get slid into the scintillator. We plug in SIPMs. We have here preamps. So this amplifies the silicon photomultiplier that reads out the light. And then you have to have your control and bias and stuff like this. So this is all done, and then we slap on some covers, and then these go on the outside. So this was sort of 2020. I guess yeah, it was I think it was. I'm trying to remember. This pandemic was a blur. I think it was mostly built in summer of 2020. In that case. All right, so I just want to mention again, you'll have one of my good friends come here and give more discussion on the far carpet board region. I can't even begin to touch base on this, but I do want to emphasize, as I did yesterday, that EPIC is going to be a really long detector. It extends, almost 80 meters. I've largely been focusing on the barrel, but there are detectors and pieces that go all along the beam in these directions. And one reason is that we really want to measure all of the particles that come out of the collision. So if you only have the barrel, particle that kind of is glancing and is very close to the beam pipe won't be measured. So this is really an important part of understanding the physics that we want to do. And so I'm sure you'll learn later in the week more about all of these different calorimeters and other detectors such as the Roman POTS. All right, a few other experimental concerns. I've largely been talking about detectors. And they sort of, and thus far in the school, they've kind of existed in sort of a magic realm where they're just sitting there and like we're getting information from them. So one thing is, and people haven't asked so much, oh, a little animation didn't quite. Oh, I see. I deleted the one with the crab crossing. Oh, I'll have to post this again with the right animation. Now I'm a little sad. All right, fine. So you can ask yourself, all right, I showed you this picture and these beam lines are not, they're at an angle from one another. And so you could be like, well, why would you want to do that? So right now, the way Rick is running, at least in STAR, the beams are basically aimed directly at one another. So you have a collision happens hopefully at the center, particles come out. But you can also angle the beams, so now they're not quite at a straight line. So you still have a collision in the center, but what this does is this narrows the Z distribution of collisions that you can have. But and we're actually doing that for S Phoenix right now, but we have a very small, I think 2 millirad crossing angle. Here we're proposing this high crossing angle, and the issue is so if you have your bunches, and so this actually really shows the beam is always bunched at Rick, and this will be true for both the electron and the ion beam. When they cross like this, the probability of interaction is basically the cross section of these bunches. Well, if they're aimed like this, you actually get a lot of luminosity loss due to this crossing angle. And so we have these crab cavities, and I'll post this with the animation, that basically takes the bunches and rotates them as they're going into the collision. So then they come in, instead of coming in at an angle like this and crossing, they actually really come in at each other head on. And this actually preserves the luminosity, since one of the key aspects, if you recall from yesterday, of being able to do all the measurements that we want to be able to do with the electron ion collider is to take enough luminosity. Otherwise, it will take us many, many more years than we have planned to actually make all of the data. And then, not only will I be retired, but maybe you guys will be on the verge of retirement at the end. So we definitely want to measure luminosity fast enough. Maybe I'll just not, I deleted it from the thing. All right, fine. Back it up. All right, and then maybe this also allows us to bring the focusing magnets close to the IP and stuff like this. So there's an interesting aspect to this. All right, another thing that we didn't really discuss is, right, this is actually, and you saw it a little bit in the photo of the S Phoenix CBC, but if you have a detector here that's at the center, and now you have signal and cooling and everything else and power to it, I mean, you have to weave all of that through all of the existing detectors here. So this is why you might ask, why are there dead regions in a color emitter, for instance? Well, if you put in your very nice vertex detector at the center and you don't leave a way for the signals to get out, then it doesn't really matter what it's doing. And so this is actually a really big job to keep track of all of these different subsystems, because each subsystem is kind of a separate project. Somebody has to keep track of where we're planning on putting posts for cooling or pipes for cooling or support frames. So these things need to be supported. They're very heavy if you think about it, and so you need some support frame. And so you don't want to put a support frame piece through where someone else is going to put their cooling and stuff like this. So this is really important thing. The other aspect is, of course, this is dead zone if you have something like this, and so you really want to make this as small as possible. But if you make it too small, then you're out of luck, and you might not realize that until after everything is built, which would be a terrible time to build it. So this is really very clever engineering integration that's required to optimize everything. And so this is something that is often not discussed in the physics context, but is one of the things that at least makes me lie awake at night when I'm talking about detectors, because it's just a very complicated and interesting problem. Another issue is background radiation. So there's radiation that can damage your detectors and also cause background signals. So there's 3 types of radiation that we worry about. One is radiation that's associated with the primary collision. So this is just your bunch-to-bunch collision that you're expecting. Another is synchrotron radiation, and another is beam gas induced. So these kind of couple with the beam parameters. So higher luminosity, the more primary collisions there are, the more synchrotron radiation there is, the higher the probability of beam gas there is. And so, you know, you could ask, well, why is radiation bad? I mean, so part of it is the occupancy of the detector. I mean, radiation is basically particles. So, so if you have something, you have a detector that's to measure something, if you have radiation, it will measure that. So you get additional hits in your detectors. This can especially be bad for the tracking and vertexing layers that are really close to the beam pipe. And it can also, these particles can, even though that radiation, for instance, is like synchrotron radiation is largely photons, for instance, you still get scattering and secondary interactions. So this could change your PID detector, but also this starts to affect the detector lifetime. This is something we're not going to really cover here, but radiation damage detectors. So we talk about radiation hard. So this is the idea that the detector is mostly protected from radiation, but you radiate something for long enough, and it will stop working. And this is actually largely when we have shutdowns at any of the major experiments, you're often replacing electronics and other things just due to radiation damage. So you'd like this to be as low as possible. And so this just is some of the work that's being done. So this is just plots now of the primary collision. So this is photons and charged particles. And what this is showing is for the different luminosities, so the difference between photon accumulated dose. So this is the radiation that just comes from photons. This is the radiation that's coming from charged particles. So you can see here the dose is along the z-axis. This is the z-axis of the plot. Then the z, which is the up and down the beam pipe, is the dose you get through epic. And then r, this is the distance from the beam. So as you expect, less of an issue here. And then you can see that even the detectors themselves change the dose that you might receive. So if you, for instance, are worried about like photon dose, if you're on the outside of the barrel calorimeter, you can see this really blocks a lot of photons. It shouldn't be a surprise. This is the barrel calorimeter is an electromagnetic calorimeter. It's built to block photons, so you expect less of them to come out. This is easier to simulate in a way, because this comes from the primary collisions. Those are at least reasonably well understood with simulation. Neutrons are also an issue. Neutrons will damage, your readout electronics, silicon photomultipliers and such, so you can make these different plots here. And they actually look different. These are set up for 6 months of running at a particular beam. And so these are two different beam energy, collision energies. And so, for instance, silicon photomultipliers are often used for readout or damaged by neutrons. So this is just an important thing to consider. Lastly is the synchrotron radiation. And so electrons will, of course, produce synchrotron radiation. We have here some modeling that you can see here. There are ideas in terms of what we can do to absorb this. So for instance, this is the idea of coating with gold. So this is the difference you get in the various subsystems. If you have no gold coating versus if you have 5 micrometer of gold coating on things, you can see it knocks down the synchrotron radiation in different areas. So there's different things we can do that are still under study to deal with all of the radiation and issues that happens that you need to take care of in order to be able to do the physics. Last but not least, I know I'm running a little bit slow, is beam gas issues. So the beam pipe is a vacuum. We do pump it out. It takes a while, but you'll never be able to make something a perfect vacuum. So there's always gas in your beam pipe, and now you're running a beam through it. So there's always a probability that the beam will hit gas in the beam pipe, and then this causes a collision, just like a regular ion collision that you might have in your detector. And then there also is an issue that you might have to worry about. So and one aspect of this that's really quite important is this is showing for the different collision energy possibilities. So this is the hadron on electron. This is the collision rate of your DIS. So this is your electron on proton, what we all know and love. And this is showing the collision rate of the hadron beam gas events. So this is the probability of the proton running into something random. And this is down here, this is just showing the electron beam gas events. And now if you look at this number compared to this, the beam gas collision rate is actually much higher than the physics collision rate. So this is something that will actually require a lot of clever thinking to deal with, mainly in terms of not swamping out our signal with background. All right, so we basically got here some final thoughts. I have one more slide after this, but so really, in order to be able to answer all these fundamental questions, to determine the answers to how the fundamental structure of nuclear matter is, we really need to understand what the kinematics of everything comes out of collisions and the flavor. And so you really need to have this optimization where you're optimizing cost, speed, resolution, robustness, technology interplay. So that's actually a very complicated, and in my opinion, a very interesting problem. And you know, that's something that goes beyond just the physics work. And there are actually pieces of EPIC that already even exist now that exist and they're working well, from the HCAL to some test beam prototypes. And we have test beams that are ongoing. So simulation is great, but nothing beats reality. So we really do build sections of these subsystems and put them in a beam and like with particles and see what actually happens. And one thing to note, these detector subsystems are essentially separate projects. So each one has a team of people working on them, building them, calibrating them. I didn't really talk about that, but it's actually quite an endeavor. So lots of things I didn't cover. I think some of this you'll get to, but they didn't talk about readout electronics, data acquisition, the streaming readout, how we combine data from tracing clusters and jet finding and all that other good stuff. I didn't talk about the far forward and backward regions really. I showed you the measurements we make. We actually correct our measurements so we can unfold for things. They didn't talk about that. Probably I'm missing something else. This is a lot of years working on detectors. So you can see if you go from a bright face graduate student to an associate professor, you can see what working on detectors may do to you. Hopefully I see some of you joining me in the experimental hall or calculating things that the rest of us can measure. But thank you.
Go back to the calorimeter at the hadron and cap. One question. Yeah, yeah, that one. So it's a frame with scintillating fibers inside this.
Yeah, so each of these are like a block, and then those blocks get put into like there's an overall frame that holds each of the blocks in place.
But like, so each one of them is 2 centimeters by.
Yeah, they're like this big.
So why are you using fiber instead of just using scintillating material, like a block, a crystal or something?
So you need something heavy enough to make the shower happen. So you need something with a lot of electrons that will cause the interaction. So if you just have scintillator, the particles will just come through, and all you can then do is count how many of them might have come through, but you don't know their energies. So you really need something with a lot of electrons, something very heavy.
So the frame is the one that's.
So the dark material here is tungsten powder. So tungsten is really heavy, it has a lot of electrons. So your electrons or photons are hitting it will really lose all of their energy in that block.
But then why do you use fiber inside instead of say scintillator to read out the light?
So I think what your question, so the fiber, really the answer to your question is money.
Is fiber cheaper?
Yeah, so what we could use if we had a huge budget is these crystals, right? So lead is also very heavy. So this lead and tuxinate crystal, instead of having something where you don't get light coming out, so light come out throughout the whole crystal. So this is something that you could have used instead, but these are very expensive. And they're also very heavy. There are other reasons why you might not want to use this. So this is a much cheaper technology, and it's not 100% clear whether we need an electron calorimeter in the hadron end cap. There not many electrons will go there. So we don't want to necessarily spend a lot of money on a detector that might only have somewhat of a marginal usefulness. But you really want to spend as little money as you can get away with that still achieves all of the physics objectives that you need to do.
How do you control the stochastic term and resolution? Like, why does it vary detector to detector? You made it sound like it was kind of an unavoidable.
It is largely unavoidable. Let's go back to the. Am I going? Am I going the right way? Haha. All right. So one way you could change this is in your choice of material. All right. So and how long you have your calorimeter, and whether it's, for instance, sampling versus not. So for instance, if you built a really long calorimeter out of the lead glass that I was showing, the stochastic term would be relatively low because everything that hits that will always lose all of its energy within the glass, and you'll measure all of the photons that have come out. And so that will be better. If you have a sampling calorimeter, you can't measure the photons that are basically going out in the tungsten or the lead or whatever it happens to be. And so then you have higher fluctuations. So this is the same way if you have measured 10 of something, you know that the statistical fluctuation on 10 is going to be 3. But if you have 100 or something, it's 10, which is 10% as opposed to 30%. So basically, the more of the light you can gather, the smaller that term is. But you can't get away from the nature basically. So quantum mechanics is, as far as we can tell, the way the universe works. So
It's basically just like the shower to shower fluctuations, and a shower depends on detector.
yeah, so the shower depends on the detector. So yeah, the only knobs we really have is how big a detector to build and what material to build it out of.
Right, let's thank Rosie once again.
Announcements, if you need a USB, I have them here. There's still 2 wandering around. If I could get those back at some point. Take a look at your draft certificates on the web and the student presentations. I'm going to start posting those. So if there are any corrections or anybody